Okay, so now I'm going to try and rattle through a few examples of using combinations and permutations. So the first example I'll do will be, start sort of easy and get a little bit more complicated as we go along. So the first I'm going to go for is just working out what's your chance of winning the National Lottery. And I mean the jackpot to the National Lottery. Okay, so the National Lottery, you can look here, Lotto, is essentially a lottery in the UK where if you get the first 6 numbers to come out of 59 correct, then you win the main overall jackpot for that lottery. Okay? So, essentially what it's asking is, what is the chance of choosing 6 balls correct out of 59, okay, that are taken out at random. So here all we need to do is count the number of ways you can take 6 balls out of 59, okay, and since there's only one way of winning, okay, we've counted the correct number of winning combinations, and of that there's 1, so it's 1 over the total number of combinations is the chance of winning the National Lottery. Okay, so what I'm saying is the probability that you win, okay, is equal to 1 over the number of winning draws, or number of draws that you can have out of the lottery. Okay, the number of draws that you can have is the number of ways you can choose 6 items out of a list of 59. So that is 59 choose 6. Okay. One thing to say is that notice that order doesn't matter in the National Lottery. It doesn't matter if your number came out in exactly the sequence at which you bought the tickets or any other sequence. Okay, each of those would win for you. Okay, so and then we can calculate over here the chance of winning. So it's the combination of 59 and 6. Okay, which gives us this number that's about 1 in 4.5 million. Okay, so if we look at the wiki page for the National Lottery, you can see that that also agrees with the number that we're given. Okay, alright, okay, so let's do a different one. Here's a kind of typical sort of example sheet quick exercise question. So how many words, distinct words, can be made from the letters B, A, N, A, N, A. Okay, so we take the word banana, and how many other distinct words can we make? And I don't mean word like it's in the English dictionary, I just mean a combination of the letters that isn't repeated. Okay, so how do we answer that? So we can think of our different, so essentially we've got one combination here that consists of one B, one A, okay, one N, okay, which I'll write with the circle with a cross, another A, another N, and an A. Okay, we're looking at all the ways that we can combine these 3 distinct colours out of these 6 potential spaces. Okay, so in other words, we're thinking of how many ways we can order the numbers 1 to 6, okay, into bins, okay, of size 1, 3, oh, of size, well, 1, so we've got space for one element, size 3, size 2, okay? So all the ways that I can put these numbers into these distinct lots of numbers of ways I can organise these letters around, okay? So what I'm pointing towards is this is going to be some sort of multinomial. In particular, there are 6 letters, okay, to choose from, and then 1 letter that accounts for the B, 3 letters that are the same, that count the same order no matter how they come out for the A's, and then finally 2 letters for the N's, okay? So then we're going to get, I can probably do this one in my head, so we're going to get out of this 6 times 5 times 4 divided by 2, just cancelling this out with the first few terms in here, so we're going to get 60, okay? Alright, next one, which we can't do in our head as well. Let's consider the game of draughts. Okay, so just to look up here, so draughts. Okay, so draughts is a game which is played on the black tiles of a chessboard, okay, and there are 12 white checkers or pieces and 12 black pieces, and I'm asking how many ways, without removing the with 12 white pieces and 12 black pieces, can I rearrange onto a board in a legitimate way, okay? So it's a similar question to the banana question, actually, just on a slightly bigger scale, okay? So think of it this way, so how many checkers or draughts, so 2 different names for the same game, draughts layouts are there, okay? So well, we've got 64 tiles in total on a checkers board, but only half of them we use, so we've got 32 tiles to use them between, okay? And then what we think of doing is we're going to decide that 12 of them are going to be white, so we've got 12 spaces here, 12 of those 32 places we're going to put in a black, and then with the remaining 8 spaces, okay, so we have 12 white, 12 with a black piece on it, and 8 blank, okay, right. So essentially it's the same idea as before, we're just essentially partitioning up the tiles, the numbers of the tiles, into distinct pieces based on whether they're white, black or blank, okay? So again, the answer is going to be a multinomial again. We've got 32 things here, then we reorder to eliminate 12 things that are white, 12 that are black, and 8 that are blank, okay? Now, and what I'm going to note here is we're going to end up with a reasonably big number. So if I just do the calculation here, okay, so let's get the factorial function. Okay, so I've got 32 on the top, and I divide by factorial 12 times factorial 12 times factorial 8. Okay, and here I get a very large number. And something you'll realise that's a bit strange is we've got a 0.04 on the end here. Okay, that doesn't seem particularly good. And that's essentially because 32 factorial is an enormous number. Okay, so something to the power of 2 times 10 to to the power of 35, so enormous number. We'll divide it by a further enormous number. Okay, so sometimes I have to be a bit careful with these things with computation, because if the computer's not dealing with integers and having to round things, then sometimes these errors can creep up from these large numbers. Okay, so one way maybe around this would be to do the following. Think of this as like we choose which tiles, say, are going to be blank, and then choose, say, between the black and white tiles. So think of it this way, that we'd have 32 divided by 24 factorial, 8 factorial, okay, and that's the number of ways of choosing which of the 8 tiles on the board are going to be blank. And then amongst the 24 that have got a piece on them, I've got to decide how to reorder, okay, those 12 pieces of each type. Okay, and notice this is exactly the same expression over here. So I've then got 32 choose, let's say 24 or 8 times 24 choose 12. Okay, and that's going to work out a little bit better for us, because we're going to end up with two smaller numbers multiplied together rather than a large number divided by a large number. Okay, so if I do 32 choose 24 times the number of ways of choosing 12 things out of 24, okay, I get a nicer number with lots of zeros at the end. Okay, it doesn't have this sort of rounding error issue. Okay, all right. Next, the following is quite a famous example. Okay, so in a football game, so that consists of 23 players, including the referee, not including the linesman. Okay, so in a football game with 23 players, okay, what is the probability that two players have the same birthday? Okay. So I'm going to answer this question by asking, what is the probability that two players don't have the same birthday? Okay. So all got different birthdays. When I say two, I mean two or more. Okay. So they've either all got different birthdays, or two or more players have the same birthday. Okay, so what we have is the probability of two more having the same birthday plus the probability they all have different birthdays is equal to 1. Okay? So why is that? Because remember, this is the sum of all the outcomes that there's a different birthday. This is the sum of all the outcomes where two or more have the same birthday, and those two sum out all the different outcomes that can occur. We know from our rules of probability that the sum over all the outcomes must sum to 1. So that's why this holds. Okay? So the probability of two or more having the same birthday is 1 minus the probability they all have different birthdays. Okay? So the probability two or more have the same birthday is 1 minus the probability that are all different. Okay, so let's work out the probability that of the 23 players, they've all got different birthdays. And again, we're going to use our trick. We're going to count the number of ways that they can all have different birthdays. divided by the total number of birthday combinations that we can have. So the number of birthdays. Okay. So if we're going to count up the number of birthdays, we could sort of line up the players 1 to 11 of the first team, then ask the referee his birthday, then line up the opposing team and ask them players 1 to 11. Okay, so there are 365 birthdays that the first player could have, and then for each of those, the 365 birthdays that the second player can have, and so forth. Okay, and I'd end up multiplying this 23 times. So 365, okay, to the power of 23. Okay. Next. Now let's imagine we ask them and we want to count all the ways that they can be different. Okay. So I'd ask the first player and the 365 days which he can use which are not currently occupied by another player. Okay. Then I ask the second player, okay, and there's one day that's occupied. Okay. So there's 364 days they're allowed. Okay, and we're kind of ignoring leap years and all the rest of it. We could, okay, could work a bit harder and get that to work out as well. Okay, and we keep on asking, okay, till we get all the way down to the very last player. So we get 300 minus 23, well, minus 22 really. Okay, 342. Okay, or in other words, what we're going to get is 365 permutation 23. Okay, there's a number of different birthdays that number of ways that everyone can have a different birthday. So the probability of all different birthdays is given by this. Okay. Okay. Right. So let's do the calculation here. Okay. So the number of ways we can choose different birthdays from all the players divided by 365, okay, to the power of 23. Okay, let's get the answer from that. We see it's about a half. Okay, which might come as a little bit of a surprise to you. Okay, but notice what we're doing is if we look at these numbers, we've got sort of 365 divided by 365. Then we've got 364 divided by 365. Then we'll have 363 divided by 365. And then finally 342 divided by 365. Okay, so all these numbers are reasonably close to 1 when I divide them out. Okay, so when I divide this by this, I'm going to get a bunch of divisions which are close to 1. Okay, getting a little bit smaller each time, but when I multiply them all together, we're going to see that it only knocks off about a half off the total. Okay, so we get about sort of 0.49 out of here. So the probability that two or more players of the same birthday okay, we're going to get a little bit over a half. Okay, so there's about a 50-50 probability that in any given football game that two players or the referee share a birthday. Okay. Right, and then one final question or exercise. Okay. I'm going to suppose that we're going to have there's going to be a party. Okay, and in that party there are going to be 5 tables. Seating 8 people. And to the party there are going to be 10 feuding families. And I mean feuding, they're feuding amongst themselves. Okay, they're families, so they have to sit on the same tables together. Okay, but I'm going to assume that to each table, okay, must contain 2 families. So each table contains 2 families and no 2 family members sit next to each other. I'm going to ask, how many ways can this happen? And I'm going to specify the question a little bit more. I'm going to assume that we're going to label the tables sort of A, B, C to E. Okay, and then on each table there's numbers for the places, sort of 1, 2, 3 up to 8. Okay, so there's a specific order associated with the different places. Okay, that sort of slightly makes sure that we sort of concretely do the question in a good way. Okay, so first thing that we want to do is we kind of essentially have our 10 families, okay, and then we're going to put them in pairs, okay, it doesn't matter what order they go in, into the different tables, okay. Okay, so essentially what we're going to do this, we're going to sort of break this question down into 2 parts. One question about the tables, another question about the layouts of the individual tables, okay. So the number of ways of splitting 10 families into sets of 2s, okay, is going to be 10 factorial divided by 2 factorial for each of these unordered sets to the power of 5. Okay. Then we're going to ask, within a table, okay, there's going to be 8 spaces, 1, 2, 3, 4, up to 8. Okay. And now let's suppose we've got sort of family A and family B. Okay. So in the first, we want to order them so no 2 family members are sitting next to each other. So let's suppose the place number 1 belongs to family A. Okay. So there's then 4 people who can go in this position. Okay. And then for the second position, there's 4 people who can go in this position. Okay. And then for the third position, well, there's 1 family member from family A taken out. So there's 3 people who can go in this position. Similarly, 3 from this. And notice we can go all the way down to 1 and 1. Okay. So the number of ways I can order, so it's family A, family B, family A, family B, is 4 factorial. Okay, for each table setting. Okay. Then notice that's from family A, family B, family A, family B, but we could also do family B, then family A, then family B, then family A. Okay, so there's twice as many outcomes for that reason. Okay, so from this, okay, we'll get an answer, and we can do this for each table independently of all the other tables, so it doesn't affect what goes on at one table, doesn't affect the combinations of the other table. So we're going to get 4 factorial times 2, okay, and then for each table to the power of 5. Okay, so what we end up with is 10 factorial, okay, this 2 is going to cancel with this 2, times 4 factorial to the power of 5. Okay, so let's just check what that is. So 10 factorial 10 times factorial 4, and we'll put that to the power of 5. Okay, which gives us a rather big number. Okay, right, okay, that'll do for now. Okay, that gives a fairly good overview of the different sorts of tips and techniques we can use in order to do sort of counting with different types of examples. Okay.